Okay, we're ready to roll. Good evening, everybody. As this part of the slide says, my name is Steve, and as this part of the slide says, I'm a little bit of a geek. Now, if we've all turned up to the correct room, you should be expecting a talk about Ada Lovelace and the very first computer program. Now, clearly, I am aware this is the last talk of the day, and I am the only one between you and the pub. Therefore, I shall try and make this interesting and entertaining, or worst case, quick. So this is me. What we're going to talk about? Well, over the next 50 minutes or so, I'm going to give a brief introduction of who Ada was, the time that she grew up in. I'm going to look at that first program that she wrote. What does it do? How does it work? And then we'll look at transforming that program into the one and only true language, which is JavaScript. Now, we've got a code of conduct. No naughty words. We'll look at how it works, we'll put it into JavaScript, and then we'll cover that thorny little issue of, was Ada really the first programmer? But before all of that, who am I? What have I done to earn a place on this stage? Or as this should be called, the ego slide. This is where the speaker will brag about themselves for 10 minutes while everyone goes through their phone looking what's in the other room. I'll give you a clue. In the other room is also someone called Steve G. If anyone is now thinking I'm with the wrong Steve G, they're there. So who am I? What have I done? Well, I am a general purpose developer. I've always been a developer. I've done the junior developer, medium level, senior developer stuff, CTO stuff. It's always development. It's never marketing. It's never sales. It's always building something, because that's what I do. It doesn't matter what I build. Doesn't matter what platform I'm building it on. If I can write some code, I'm a happy bunny. I'm also an author. I've just finished writing my 6th book on computers and technology. This particular one was on old computers. As you can probably tell from the title, 20 go to 10. Any computers were out in the 80s, that book's probably got it in. I like that stuff. I like emerging technologies because I like new stuff as well, and I speak at various conferences. FOSDEM, for example, is this weekend, and I'm heading there right after this conference. Oh boy. I also give talks at the Computer History Museum in Cambridge. Mostly school kids, they come round, I tell them about the history, what computers were like, and they go, what, this size? Yes, that size. And all this sort of thing. But none of that's important. You can ignore everything there, none of that's important. What's important is not what is not written on that slide. I'm not a professor of computing from Cambridge who studies the history and theology of what computers were like. I'm not a history professor who understands the minutiae of Victorian society. Everything I'm going to show you is stuff that I have worked out myself from first principles by looking at the program and just reading books. That's a very long-winded way of saying, if I can do this, anyone can. So what can anyone do? Well, let's start. I'm also an AFOL, by the way. Anyone know what AFOL stands for? Adult Fan of Lego. This is made from Lego. This Ada is fully Lego. This Ada is crochet. Say hello, Ada. Doesn't talk. So that's me. That's my Lego Ada. So this is probably one of the most famous paintings of Ada. She was born in 1850, died 1852. If you're doing the maths, yes, that is a very short lifespan. And her name is not Ada Lovelace. It's Augusta Ada King, Countess of Lovelace. So what things do most people know about Ada? If you were in a pub quiz, then question 1, round 1, would probably mean, when was she born? When did she die? What else do you know about her? Probably these 3 things. She was the daughter of Lord Byron. Lord Byron, yes, it's that Lord Byron that does the poetry stuff. They didn't really have a relationship, though, no father-daughter thing, partly because Lord Byron wanted a boy, which is why he called her Ada, although she's really Augusta. And also, he died when she was 8. And even then, he didn't spend a lot of time at home. He liked spending time... He didn't really like spending time with his wife. He liked spending time with other people's wives. There is lots of words for what Lord Byron was, but we have a code of conduct, and I don't think I'm allowed to use any of them, except perhaps the phrase scoundrel. That was Ada's father. Her mother was Anne Isabella Noel Byron. And being married to a lord, she was a lady, but she went by the name Baroness Byron, or the 11th Baroness of Wentworth. And yes, I'm having to check this up, the 11th Baroness. Ada did end up marrying a lord. That was the first Byron of Lovelace, which is how Ada becomes known as Ada Lovelace. And you're thinking, okay, already we're marrying into some money here. They were a very well-known family, and obviously with Lord Byron going off wherever, she became quite infamous in her own right, because they wanted to talk to her about her father, essentially. This was Victorian society at the time. But she was taught by people like William Friend, who was a Cambridge professor, who also taught her mother. She was also taught by William King, who, by the way, is not the same William King that she married. That's a different William King. That was the Lord William King. And also she was taught by Mary Somerville. Now, some of you might know the name Mary Somerville from various science documentaries. Mary Somerville was a scientist in her own right, was also one of the first women to be allowed into the Royal Society. Because at that time, the Royal Society didn't allow men, but they'd forgotten to write the rules in the rule book. So they got in. The men of the group then had to rewrite the rules to kind of get rid of Mary Somerville, and then she could come back a few years later when they finally woke up. What's interesting about that bit, it was Mary Somerville that introduced Ada to Charles Babbage. Charles Babbage was what posh people are called eccentric, or they're a bit of a character. Poor people with the same personality are called not-so-crazy. It's a Victorian class thing. And he was very good at building machines. He was interested, as an engineer, of automating things. Needed money for this, and he wasn't interested in being polite to get the money. So eventually the money sort of dried up, and a lot of his inventions and creations didn't come to pass. But it was through Mary Somerville that Ada got to know Babbage, and it was and in June 1833, she got to see the prototype of the difference engine. And that later led to her working on more of Charles Babbage's work. Also interesting point about that. No, we won't bother with that. Actually, I can't click on that. So that was her, and yes, we think of her as the first software developer, but we'll come to that at the end to say, was she really, though? So that is what she did, and this is what she programmed. There we go. That's the very first computer program ever written. Well, it's what I said I'd do in the title of the talk, right? So I've now fulfilled my obligation, and we can all go down the pub. Oh, you want an explanation of this thing as well, do you? Okay. So this was not downloadable from the internet. She hadn't invented the internet at that point. But this was the program, and this was Note G in an appendix in a translation of a book. Okay. A note in an appendix and a translation of a book. So chances are you would not have ever seen this book. The book was written by Luigi Federico Menabrea. It was the notes which he wrote from an 1840 lecture that Babbage gave in Turin. Menabrea was quite well known as a master philosopher at the time, and he also became the Prime Minister of Italy a few years later. So already you can see the sort of circles that all of these people are mixing in. Minor people like Michael Faraday and Charles Darwin were personal friends of Ada's and the family. So, social networking in those days was a little different. But Luigi, who became Prime Minister, wrote a book based on Babbage's lecture about his machine. And Babbage says, hey, this book is written in foreign. We want an English version. Can you write it? And basically that would be Babbage. He, very good at technology, not very good at being sociable or polite. And Babbage, because he knew Ada and he knew that Ada knew his work, so he thought she's the perfect person to write this. And she did. Although in the process of translating it, she made the book 3 times bigger than it was originally. Because there were so many things that were in the book which were technically correct, but just didn't fill in the details. It was like saying, here is a stage, but then not describing the stage, its size, its color, its height, all the interesting, important things. And in part of that translation process, she added all of this material. And in the back, in the final appendices, you have a series of notes that explains, in her ideas, how you could program this machine. and this was note G. There are several other notes that precede this that contain portions of this. So there's a section that just contains this sort of little section and then an explanation of what this is. But this was the culmination of that whole section. That is the program. So what does it do? It does some mathematical things. In mathematics, the Bernoulli numbers are a sequence of rational numbers which occur frequently in analysis. And as most of you mathematicians here will know, the Bernoulli numbers appeared in the Taylor system expansions of the tangent and hyperbolic tangent function in Faubourg's formula for the sum of the nth powers of the first n positive integers in the Euler-Maclaurin formula and expressions for certain values of the Riemann zeta functions. If anyone wants an explanation of that, they're going to have to give that to me. I have no clue what that is. But it's something mathematicsy, and it is something that produces these numbers. And you'll notice there is nothing special about these numbers. They're not numbers that you just go, oh, right, I obviously can see the pattern here. There's no obvious pattern in these numbers. The only thing you will notice is there is no reference here for 3 or 5 or 7 and so forth, because after 1, all of these other alternate values are 0. So sometimes when you're looking up maths books about Bernoulli numbers, sometimes they consider this the 4th Bernoulli number and this the 5th, and sometimes it will be the 6th Bernoulli number, just depending on how they decide to count them, whether they think zeros are important or not for their application. So they're all rational numbers, they're all computable, they're all fractions, but maybe the decimals have a clue to the pattern. No. There's no pattern there either. There's nothing to give us a clue on how do we get to the 18th Bernoulli number. Well, there's a reason you can't just get to the 18th Bernoulli number. It's because you've got to go through all of the other Bernoulli numbers to get there. That's the same as Fibonacci numbers. If you've got Fibonacci sequence 1, 1, 2, and then you add the 2 previous numbers, 1 and 2 become 3, then 2 and 3 become 5, you've got to compute all the previous numbers. You have to do the same with Bernoulli numbers. So we know it's some fractional things, and this is the fairly obvious formula, I think you'll agree. Now, I hope you're taking notes on this. Now, this formula is fairly straightforward, because if you start breaking it down, you've got this little odd term here, which you think, oh, there's nothing to it. And then you've got the previous Bernoulli number with an equation, plus another Bernoulli number with very similar 2n, and then you've got some extra multiplication terms and some extra terms up here, all following a pattern. And then when you add the next Bernoulli number here, you've got the same pattern again with some extra terms. So you can see how this very easily would lend itself to be a programmable solution. So it seems fairly obvious that this problem of computing Bernoulli numbers should be done by a machine. And this was Charles Babbage's want throughout his career, was to automate processes. It is believed that when Babbage was reading through books of logarithms, which did the same things, they were just big lists of numbers, which mathematicians hated calculating, so they just bought a book with the numbers pre-computed. Well, he found that these pre-computed numbers had errors in them. And we know why there are errors in them, because humans did it. Humans did the maths. They might have made a mistake in the maths. Humans copied the maths into the printing press. They might have made a mistake there. The press might have got the numbers. There were so many opportunities to get things wrong. Babbage says, let's just get rid of humans altogether. We can automate this process. And that's what Babbage wanted to do, automate process for numbers, to compute numbers. So it was natural to use Bernoulli, for Ada at least, in demonstrating what a machine could do. Now, we've just rearranged the formula on the last slide to make it, even simpler. You can see that everything just breaks down to subtracting another number from the term and dividing by yet another number. So as we're going on, you can see that we need, essentially, an array, a count of where we are, and then just keep subtracting numbers, one after another. And if we lay it out in this way, you could pretty much see that you could write this on BASIC on a Commodore 64, and it'd have no problem with it. And this is all it's doing. So if it's this easy to code, well, and we've got no computing devices or calculating devices, we would normally do it by hand. But we're not going to, because we've got a machine to do it now. So let's go back to the program. How does all of that compute the numbers? Now you know what the sort of formulas are. You'll probably notice in this column here, you've actually got little comments on what the formulas are happening at which point in this program. It's like a comment, right? I'm re-emphasizing the fact this is a comment in case you've never seen one in code. Because we all write comments in our code, right? I was expecting a louder yes for that one. We all write comments in our code, yes? Yes. You don't sound very convinced about that, but we'll let it slide. So what does it do? Let's take a portion of that and we'll break it down. Each column is exactly the same. So in the first column, we have what is essentially a line number. It's the number of the operation. If you remember programming in BASIC, your first line was 10, your second line was 20, and so on. She's done the same thing here, but because it's not BASIC, they don't go up in tens. Next is the nature of the operation. What are you doing? Multiplication, subtraction, addition, and I think there's one down here, addition and division. 4. 4 operations are the only things this computer does. Add, subtract, divide, and multiply. Nothing else. Then we have a list of the variables that are operated upon. And here, I know it's a 200-year-old document, but it's v2 times v3, v4 minus v3, and so on. That's your basic instructions. Next, we have the variables receiving results. So if we do this computation, we then assign it to the variables here. Here, we're assigning it to 3 separate variables. There are still very few languages that allow you to do this sort of jiggery-pokery, and this is the only line in this program where she does this. It just saves time. If this were a real machine, these numbers would be stored as the position on a gear wheel. And if you're turning the gear wheel, it takes a lot of energy to do that. So let's have one operation where you can turn 3 gear wheels together to assign one number to 3 variables at the same time, because it's quicker than setting one of them, then copying it to the next one. But of course, it wouldn't be possible to copy it because we have no assignment. We have 4 operations, add, plus, divide, and multiply. We do not have assignment, so we wouldn't be able to do that anyway. Next up, we have the indication of the change in the value on any variable. What does this mean? Well, up here we have the number 1. That means this variable has been changed once. After a couple of times, we see we have a number 2 attached to the variable. It means that particular variable has been changed twice. This is a nice self-referencing manner in which you're able to say, have I done it right? Have I used the correct variable? Because I should know at this point if I've changed it 2 or 3 times. When you dry run a program, for example, you might like to have a little note in the margin saying where you've got to making sure the machine does what you think the machine is doing. She's put it right there in the source code. And then this final bit here that we'll look at, equals 2n, equals 2n minus 1, equals 2n plus 1, is what the calculation is actually doing. It's a comment. It's a line-by-line commentary of the whole program. And you'll recognize the 2n's plus 1's from the equations we've seen. So here, she has commented every single line. That's your statement of results right at the end. She's done it. So the bit we didn't have in there was the initialization, right? We know we don't have any initialization because we don't have an equal sign. So there is no way of initializing any variable to any other. So how do we sort of kickstart this process into moving? Well, we hard code it. So up here, we have variable 1, and we've got the number 1 inside it. That's set up by the operator at the very beginning, and it stays like that for the rest of time. Variable 2 has the number 2 in it. That's set up at the beginning, and it stays there forever, doesn't change. Variable 3 is n. Which Bernoulli number are you trying to calculate? If you're trying to calculate the 3rd Bernoulli number, we put 3 in there. If you want to calculate the 4th, we put 4 in there, and so on. It's all set up at the beginning. Everything else then comes from those magic numbers. So at the beginning, you can see we're setting up 1 and 2 for the variables, and 4, which is the Bernoulli number we wish to compute. You'll also see she comments on what the variable is meant to do up here, to saying that this variable 4, will end up with 2n to begin with, and then switch to 2n minus 1. All very straightforward. We're not doing anything that's really actually that complex. The algorithm might be complex, but the actual way of doing it has been broken down step by step, so mere mortals like me can understand it. So let's look at what the program is doing. So we start off, we do this multiply, v2 times v3 goes into variables 4, 5, and 6. Variable 4 minus 1, which we know is always 1, that goes off into variable 4, so it's just like, decrement. v5, you add 1 to that, put that back into v5, that's increment. So we've now got our 2n minus 1 and our 2n plus 1. We then have this divide, which is dividing v5 by v4. We know v5 is this 2n plus 1 here, and we've got 2n divided by v4, which is 2n minus 1. So this line does 2n plus 1 divided by 2n minus 1. Ah, you spotted it as well, huh? v5 is this one, and we're dividing by v4, which is this one, which means we're doing 2n plus 1 divided by 2n minus 1, but the code here says we're doing 2n minus 1 divided by plus 1. Now, Ada, not only has Ada done the very first computer program, she's done the very first computer bug. Well done, Ada. These things do not match. Comments and code do not match. And when comments and code do not match, both are wrong. Well, it turns out this was basically a typo. It was just that this bit here was a bit wrong. So you fix that. Comments are wrong. Someone forgot to change them. It's fine. Move on. It does work. And we continue. We did next divide. So, here we're dividing by 2, which is same as multiplying by a half. No performance issues in those days about having to find reciprocals. It was all jobs were good. All done. So we've got a program, but as we carry on from that, it works as normal. So now we know what the program is going to be doing. We can dry run it ourselves on pencil and paper, and we get the results we expect. Great. Now let's simulate that in the good old-fashioned JavaScript. Now, for this, I should probably do a mini mid-lecture activity. This is something my lecturers always used to do, and they used to go to the other side of the stage to deliver something connected with the topic, but just slightly adjunct. Because what I've done here is I'm saying multiply with an x. Nowadays, we normally think of multiply being the star. But does anyone here know what the ASCII character for that star is? What number is it in the ASCII table? Now, some audiences actually do know that. I mean, there are also people that have the GPS coordinates of every train station in the UK in a file on their machine. I know because I follow them on Twitter. And I'm still calling it Twitter. Well, ASCII for the star is 42. The meaning of life, the universe, and everything, according to Douglas Adams. And who is to question Douglas Adams? What is the star also used for? Globbing. If you want to look at all the files that end in .txt, it's ls star .txt, right? So 42, the symbol for life, the universe, and everything, is the same ASCII character as the one you use for listing everything in a directory. I'm sure that's not a coincidence. There's got to be some cosmic joker out there who's designed the whole universe just to do that one gag. And I really hope that is true. So, what have we got? I've decided to use the x for multiplication instead of the star, but that's fine. We don't have assignments, as we've said, so all of this stuff can be fairly minimal. And as a side point, we don't really need assignment, because we could just say a equals b plus 0. That's exactly the same. We could have variable 1 holding 0, and if we wanted to do assignment, we just say add the variable to variable 0, and we've done it. So we don't even need that. We could even get rid of the addition if we wanted. As long as we've got negate, we can do pretty much everything. There's a whole branch of minimalist computing where you can do everything ever with one instruction, which is subtract and branch if negative. You can do every other instruction with that. The Manchester Baby computer, which was considered by some to be the first electronic programmable electronic machine, it was called the Small Scale Experimental Machine, I think. I call it the Manchester Baby. That had 6 instructions. And the way that you would do things in that, if you wanted to do addition, you would negate a number and then subtract that number from something else, because subtracting a negative is addition. So why spend all that electronics implementing an addition instruction when you can just do subtract? And of course, subtracting and finding a negative is the same thing. 0 minus something else is just negation. So as you break things down, you can see you don't need all these 4 fancy instructions. You can make do with just 1. Ada decided to do it with 4, so we'll run with that. So we have just taken our program and we've just started writing line by line, what does it do? We're putting comments in there as well, and then simulating this is very, very simple. Basic switch statement saying what operation are we doing, what are our parameters, do the computation, and off we go. Now, I'm using the temporary variable here called mil. Back in the 1840s, that's what they called the accumulator store, that little temporary working space. It was still being used in the 60s. So I've called it mil here as well. And because we've got multiple destination variables, I have a little loop at the end. And that's it. That's the program. That does these calculations. So from that, we need to go back. We've said, if we, to remind you of this, to compute the 5th Bernoulli number, we need to know the other Bernoulli numbers that came before it. Similarly, to compute the 7th, we need to know the Bernoulli numbers that came before that. So we're going to have to store them somewhere, and we're going to have some kind of loop. So Ada has the first loop. She has it here. Between lines 23 and 24, there is the phrase, "Here follows a repetition of operations 13 to 23. She's done it. She's created a loop. Problem. We've only got variables. We haven't got arrays. So how are we going to loop through things? It's just not possible. Because every variable is constant, it doesn't change. So when we're saying things like variable 4 to variable 5, we can't say the next variable in the array, because that's what we need to do. We need to have the result of Bernoulli 1 and 3 and 5 all at the same time, and we need to work out how they are. So the only way of implementing this is actually copy and paste. Take the whole lot, paste it again, and then change all variable 4 to variable 5s. If you want to compute the Bernoulli number after that, copy and paste it again. So her loop, her amazing invention, this very first programmer, not only has a bug in line 4, but has no idea how to write loops, because she can't envisage it. Oops. So let's just transform this now into something legitimate, JavaScript. So we've already got our instructions. We know what is in each of the variables. We know its purpose. So we know that variable 2 is going to contain 2 all the time. So let's force it in there. Let's hard code that. We know which our variable 4 is 2n minus 1. So let's put that in there. We know that our 2n minus 1 is just decrementing that because it goes back into the same variable. And we've got our little total because every number works from the values before it. So it's that basic transliteration of what's going on that makes this a very simple transformation process. And the link, for those that are following along at home, is I do this in about 5 or 6 steps. So I'm just taking very, very simple things at each stage to show how I've transformed the program until it looks something like this, which is passably reasonable. It goes through however many times you want. So if you're computing the 5th Bernoulli number, that goes round that 5 times, does the calculation, adds it onto its total, and outputs the result at the end. Again, notice index to result as our way of getting over that problem of variables being constant. So this is all done now, right? We can go on to this important question. Was she the first programmer? Oh boy. Now, in computing, we do have this vernacular problem, because what we think of as a computer isn't what people used to think of as a computer. As recently as the 1960s, computer was a person that did computations, mathematics, work with numbers. Anyone who's seen the film Hidden Figures or read the book by Margot Lee Shetterly will know that the computers, the people who actually did the mathematics, were women in America. But the word computer was used for people who did mathematics throughout the last few hundred years. The first use of it being used as a mechanical machine was, I think, in the 1700s. And that was rare. If you think that the book that, the note G that she wrote in the appendix of the translation of the book was so unheard of, then it's not surprising that no one was using the word computer for anything other than a mathematician. And it's not surprising at all, to be fair. But yeah, also, if you haven't seen Hidden Figures, go and watch Hidden Figures. That's the TLDR of that bit, I suppose. So all this comes back to the fact of, well, how do we define programmer? We still don't have a proper definition for computer. When people say, well, what was the first computer then? I go, well, what do you define as a computer? Does it have to be electronic? Does it have to run on a power supply? What about if it's gear wheels? Is that allowed to be called a computer? Does it have to be programmable? If you set the machine up to do a calculation, that's computing things, just like a mathematician would. So does that get called a computer? And depending on how you frame the word computer will depend on, well, whether she was a computer programmer or not. Because this fantastical machine of Babbage's never got built. So does that even count? So these are some of the arguments that get leveled either at conferences like this where I present this stuff, or from people online. And has anyone here been online? Has anyone noticed that there are people online who are just a little bit troll-like? Or is it just me? Have I got such an objectionable personality that all the trolls jump up when they see my name go on stage? No, I don't think so. I think it's full of idiots. So, after one of them, someone pointed out, yeah, but the code's got a bug in it, therefore she can't be a programmer. To which I reply, well, how can you write a bug? But you've got to be a programmer to write the bug. And I just... But, you know, it's a fair point, you know, because nobody in this room has ever written a bug. So she's not worthy of joining the ranks of us lot. No, I don't agree with that. You know, bugs, I don't like them. I certainly don't like them. But that shouldn't stop you from being the first computer programmer. Notation might be considered problematic. Well, there was no such thing as a programming language before. So what did you expect? I'm pretty sure Shakespeare's first poem was not a sonnet in the style that we expect. His first poem was probably like, I really like football, it is great. We've all got to start somewhere. It showed there was a way. Before Ada and this, we had algorithms. Algorithms existed. They were created from the East. Was it Alcalium, I think, was one of the first creators of the idea of the algorithm? But what she did is she took the idea of an algorithm and said, well, these algorithms are things that humans do. Humans get to make a choice. They get to look at this and they get to reason about the algorithm as they work. If we give a machine this algorithm, the machine has to make those decisions for us, and we have to make sure we describe to the machine exactly what we want, or it will go wrong. She really codified that idea of an algorithm. Also, the loop didn't work. Yeah, it doesn't stop her from being a programmer in my eyes, but it does say that she hadn't got all the pieces together yet. And that's fine. It's fine to not have all the pieces. Work in progress. She was translating somebody else's work, usually said by people who've forgotten that she multiplied the size of the book by 3 times. The fact that it needed so much extra work in that book to explain what really was going on behind the scenes. And this is something that Ada did a lot of later on as well. It's probably well known, I mentioned at the beginning, that her father, Lord Byron, she did get some of the ideas of poetry and love for the arts from knowing that her father was this great poet. Not a great man, great poet. I'll just clarify for any of the hard-of-thinking people watching on the video stream. She liked the arts, so she was thinking, well, I know this machine spits out numbers. We put numbers in, we get numbers out. They compute numbers, that's great. But what if that number was a word? We could get the machine to generate poetry. This was one of her ideas, because she was one of the first people in the country to actually see these mechanical machines producing things. She reasoned, well, we could generate poems or songs with a machine. She had invented ChatGPT 200 years early. She also thought, what if these numbers were notes, musical notes, so you could play a melody? She'd invented MIDI. She was also thinking about, well, if these numbers were colours, you could actually use this to paint a picture. Okay, no Van Gogh, but maybe a paint by numbers. That's where she got to. And she'd come up with all of these ideas. None of them directly related to the work that we've just seen with that program, but all thoughts about, well, what does it mean to be a piece of software? What are you actually programming? What's the purpose here? And of course, the fundamental spoiler is, yeah, but if Babbage built the machine, that means he must have written some code for it, therefore Babbage is the very first programmer. Well, let's have a look at the machine. This is the best we have. As I say, it was not built. He didn't get the money to actually go away and build this. But he is never known to have actually explicitly written any instructions on how to program this machine. He was interested in the machine for the machine's sake. All of these little gears, all of the little levers that will connect to them, he was interested in how they move and how they interconnect. There was no attempt to formalize this. He was just saying, well, yeah, if you move this lever down here, this gear will turn more. Or if you move this gear over here, these other gears will move. Not moving gears in this way is like multiplying a thing by 2, or this will do a subtraction, just these gears will move in a particular way now. That was the beginning and the end of his interest in the programming side. So if he did actually even try to formalize anything, it was certainly it certainly wasn't Bernoulli numbers. It probably wasn't even addition. I doubt whether he got as far as Hello World. He was interested in that mechanical thing and nothing else. And if anyone is actually really interested in this stuff and has a lot of time on their hands, there's a website called plan28.org. This is part of the Computer Conservation Society group to reproduce the machine that never was. Babbage created some prototypes of the difference engine, ran out of money, said, yeah, but I've got a better idea now. It's called the analytical engine, which is where this is from. But without money and without politeness, that never got built. So now is the idea from this plan28.org group that maybe they'll have another go now. Because the difference engine was built for the Science Museum in London, 10 years ago now, where they built, because obviously the full difference engine never existed, so they built all the gears, all the shafts, and they got it working. So they proved that Babbage's machine would have worked. Unfortunately, they tricked you all, because all of the cogs were not made by humans, they were made on CNC lathes. And one of the problems with that machine is if it had been built by humans, the tolerances would have been so inaccurate, the gears would have probably just got stuck. I say probably, it's very likely, and we'll never know. No one's going to have the money to do that. But it's very unlikely the machine would have physically worked, even though it theoretically definitely did. So yes, if you're interested in all of the history between that and Babbage Plan 28, it's the blog they have is a very slow-paced blog. Every year or so they do an update. So let's go back to this thing. Was she the first computer programmer? Now, we've said she came up with the idea of using words instead of numbers for the inputs and outputs of this machine to write poetry and music and probably painting as well. And every single argument about Ada, is she a programmer, is she not a programmer? More or less, never the first programmer, but just a programmer in general. But is the first programmer. And every single argument is always about, she cannot be a programmer because of this. Cannot be a programmer because of that. It's very negative. It's almost like it's on the internet. It's such a negative way of looking at things. So I said, let's turn the problem around. Be positive. Why should she be the first? What argument can I make that says, well, ignore all the negativity stuff? What could you say unequivocally that ends with a yes, and therefore Ada was the first programmer? And I reasoned it this way. Of everything that we've seen and everything that she did, creating that translation, actually filling in the gaps, explaining how a machine would actually work, coming up with that program, explaining the program, putting in the comments for that program, theorizing about how the program would be used, not just for numbers, but for arts, for writing, for music. If she had done all of that, that should qualify her as the first programmer. So think about it this way. If all of that work had been done by a man, would he have been considered the first programmer? And I think the answer is yes. I think if a bloke had done all of that, everyone would be jumping up and down going, first programmer, first programmer. And because if he would have been considered the first programmer, then she should be considered the first programmer. And this was the very first computer program by Ada Lovelace, or anyone else for that matter. So in conclusion, we can say the first programmer did some decimal approximations of Bernoulli numbers, very interesting numbers if you're a mathematician, very dull for everybody else, but they compute things that people needed. There was an algorithm that described what to do, not necessarily how to do it, just this is what you as the programmer need to do to get a thing happening, and that first programmer was Ada. So with that, I say thank you for your attention, and we may even have time for some questions. And if there are questions, we have a mic that will come roving around. You have one here. Trying to make it an easy question.
Oh, it's a dumb question. So the program was written, but it was never run.
Correct.
Got you.
Essentially because the computer didn't exist to run it on. But because we've now translated that to JavaScript, we've proven it works.
Okay, I guess a follow-on. Did she ever get to see anything of practical application with these kind of talents?
As far as I know, she got to see nothing practical. She died at the age of 36. Lots of reasons for that, lots of ill health in childhood, lots of other health problems as an adult. So all this stuff, you have to... obviously, okay, disclaimer number one. Anything I say about what Ada might have thought about the achievements, had she achieved success, did she enjoy what her work led to? One, she's dead. Two, I'm a man. This would be mansplaining at the next level if I tried to hypothesize anything that went through her head. But we know she died very young. We know that almost nothing happened in computing. I mean, one of her mathematical teachers was De Morgan, as in the De Morgan that does the binary logic rules. I think another one of her teachers was also George Boole for a while, who actually came up with Booleans. You know, the whole idea. Her teacher was the guy who invented this stuff, and even Boole didn't realize what it would get used for in computing 100-odd years later. And, you know, we're talking here, she saw the machine in 1933, this stuff was out 1940s. Yeah, she lived a few years after that, but what was the next computing innovation after that? World War II. There was almost nothing happened as far as this level of thinking went for another 100 years. So the idea, you know, even if she'd lived to 100, that field was pretty much a dead endeavor. I mean, there's lots of potential reasons. One of them is these cogs were very expensive to make. You needed good craftspeople to make them accurately enough. Although they had Boolean numbers, no one at that point had quite put the two together that if these things are difficult to make, let's just make them with two positions, 1 and 0, and use the Boolean things that her teacher invented to write this thing as a binary computer. It took a long while before anyone made that connection. And when they did, things go, oh, right, well, if we did this, then we could do that. And that was nearly 100 years. You know, you'd got Zeus, Z-U-S-E, I think, from Germany, who was creating some computers in the 1930s in his parents' basement or his garage, whichever it was. Okay, maybe that's 80 or 90 years. It was another 10 or 20 years before the idea on, oh, let's do some electronics machines that could compute this. And then obviously we get the war and everyone starts throwing money at the machines. And then this is where Turing comes into the first part of the picture. Turing at Bletchley Park, Hut 8, using the bomb to crack Enigma codes. And in fact, one of the links is Turing. He knew about Ada's work, and it was because of him that a lot of this stuff first came to light. As we say, translation of a book that pretty much got lost 100 years ago. He goes, hang on a minute, this is quite useful, this. And then other people go, oh, you're right, it is. So who knows? Maybe there was a book from 100 years before that. So that's a very long answer to a very short question. But it's me trying my best to dodge the proverbial bullet.
Yeah, I also have a quick question. So if this program was never run on a machine, and this machine never existed, what makes Ada's program different from any other previous attempts to write an algorithm or like instructions to do some calculation? Why aren't those first computer programs?
So I'll try and do a shorter answer this time. Essentially, there were no elements of prior art at that point. The algorithms that were created were meant for humans. Her one is the case of doing it intended for a machine. So whereas humans get a little bit of leeway and you can be quite flexible with how you give an instruction to a human to do, with the machine, she was very explicit about how it had to be done. And that, for me, is what separates it. You know, it's the difference between a heuristic versus an algorithm. I mean, and we know dealing with humans is difficult anyway, and a simple statement can be misconstrued in lots of different ways. This shows you, actually, let's avoid any inconsistencies, any possible ambiguities. This is how we have to at least start thinking about giving instructions to an unthinking machine. We still have a microphone that's roving, although I do know the pub is open. No. After 3, 2, 1, that's your lot. Thank you all.